Today, I'd like to finish up our discussion of chapter 17. And this is basically, continuing our discussion of carbonyl compounds. And today we're going to focus on their reactions, the reactions of carbonyl compounds with organometallic reagents. And your textbook's sort of interesting. It introduces all of the mainstream organometallic reagents all at once, and I'll follow the basic principles of what they do in the textbook, and I'll show you similarities and differences as we go along. There are a lot of subtleties in terms of reactions, so we're going to see this as the lecture progresses. So a common theme of all of the organometallic reagents is they are reactive as nucleophiles and as bases to various degrees. So let's introduce today's players. Grignard reagents. Grignard reagents really represented an early big advance in controlling organic reactivity. Prior to that, the nucleophile that people used was organozinc reagents, and they weren't very easy to control. And I think it was Victor Grignard introduced these. Another class of organometallic reagents, a biggie, is organolithium compounds. We've already seen, both in the earlier lecture and even in chapter 11, metal acetylides, and we'll take a look at them again. And finally, your textbook introduces right at the very beginning organocuprate reagents, right at the beginning of the chapter. And we'll see they're a little bit different in terms of their reactivity. So I'm going to introduce them now and set them aside. Let's take a look at an example of each of these classes of organometallic reagents. So this is an example of a Grignard reagent. It's called phenyl magnesium bromide. I'll show you how it's generated in just a second. Take an example of an organolithium reagent, one that certainly Mai has used, and I'm sure Jackson and Matt have used as well. We'll take a look at what's commonly referred to as butyl lithium, or maybe more specifically N-butyl lithium. N is the shorthand prefix that means normal, which is a way of saying linear alkyl group. Another organometallic reagent that I'm pretty sure Mai has used is Tert-Butyl Lithium. All of the organometallic reagents react with air, and in some cases quite violently. Tert-Butyl Lithium invariably, upon exposure to air, bursts into flame. And so if I'm working with a syringe of it as an air-sensitive technique, I always expect to see a little bit of fire at the end of that syringe. We already saw sodium acetylide, as I said, both in your section B and your part B of the course, and also in the earlier lecture. And finally, as I said, I'm going to set this aside as sort of separate. We'll take lithium dimethyl cuprate. And as I said, let's just set that aside and stick a pin in it until later when we have use for this. So a common theme in all of these reagents is a bond of some sort between a metal and an alkyl group or an aryl group. In other words, whether it's a benzene or a butyl group or an acetyl group. And so I can write this bond as such, as a covalent bond, but as I've said before, there are sort of layers of meaning that we always keep in our head, whether we write them explicitly or not. And so if I look at a bond between carbon and a metal group, I think that the carbon has a partial negative charge and the metal group has a partial positive charge. The shorthand for thinking about this is that metals are more electropositive than carbon. They're more willing to give up their electrons. Different metals have different electronegativities, different indices of how much they're willing to give up their electrons. So carbon has an electronegativity of 2.5. For comparison, hydrogen, which has a polar covalent bond to carbon, has an electronegativity of 2.1, or if you use your textbook table in the back, 2.2. By comparison, sodium is very electropositive. It has an electronegativity of 0.9. So a difference in electronegativity of almost 2 often corresponds to more of an ionic bond than a polar covalent bond. I haven't paid attention here to differences in the carbon, although we just take one number, electronegativity of 2.5, different hybridization of carbon is better able to stabilize electrons. So an sp hybridized carbon in lithium, in sodium acetylide, really is quite good at stabilizing those electrons. So for electronegativity, lithium, another alkali metal, an alkali metal in the second period instead of the third period, has an electronegativity of 1. Magnesium, in our Grignard reagents, has an electronegativity of 1.3. Copper is sort of special, and that's one of the reasons we're setting it aside. The electronegativity of copper is 1.9, so that bond between the methyl groups and the copper is much more of a polar covalent bond than in the case, say, of sodium iodide or sodium acetylide. So anyway, I've written this bond either without or with the partial positive charges, depending on whether you looked at my first drawing or when I annotated it. But another way to keep this in your mind is to recognize that in a polar covalent bond, you don't have share and share alike. And so we can write a second resonance structure. And so again, using this double-headed arrow to represent resonance, remember, not oscillating between, not one, not the other, not sometimes one, sometimes the other, but both at the same time, I can write this non-bond, oops, I was doing this generically for metal, I can write this non-bond resonance structure like so. Erase the stray dot. And together, these two resonance structures make up a more complete picture of the polar covalent bond between the metal and the alkyl group. In the case of sodium acetylide, we really can think predominantly of that resonance structure on the right. In the case of maybe a cuprate reagent, we might be thinking more in terms of the resonance structure on the left. So let's take a look then at the reactivity, and we'll start with a Grignard reagent. We'll start with the phenyl magnesium bromide that I gave as an initial example. And if I write one resonance structure, I'd write it like that. And we'll take a simple carbonyl compound. We'll take acetone as an example. Phenyl magnesium bromide reacts with a carbonyl compound by adding to the carbonyl compound, like so. If I were writing the immediate product of the reaction and not worrying about the mechanism, which is absolutely fine, I would write the reaction like so, with the nucleophile having added, and then you can think of the magnesium bromide forming as a counterion. Sometimes you'll see this written, and it's also perfectly reasonable to go ahead and say, okay, even though that bond between the oxygen, which is very electronegative, and magnesium really is an ionic interaction, an ionic bond, you might see the product, the initial product of this reaction written like so. And these are both correct ways to write this magnesium alkoxide. If we want to think about how this reaction occurs, in other words, to help guide our thinking, organic chemists invariably think mechanistically, whether they write it or not. We can go ahead and say, all right, guiding our thinking, or in the back of our head, we envision that polar covalent bond is like a negative charge on carbon. That carbon is thus nucleophilic, and we attack the carbonyl group, and that's what gives rise to the alkoxide anion. If you need more of a help in thinking about this, although as I said, I wouldn't generally for a Grignard reagent write an ionic structure. If you need more of a help thinking about this, we could guide our thinking with the ionic resonance structure. Maybe I'll put that in quotes just to indicate I'm really not wanting to write it this way, but just doing this to help in our thinking. We could go ahead and think about this reaction as occurring like so. These would all be valid ways about thinking about the Grignard reagent reactivity. All right, so organic chemists are very often interested in building up molecules. One of the real powers of organic chemistry is the ability to start with simple molecules and build up more complex molecules. Three of us, well, the three of your TAs and myself were all at a seminar yesterday talking about the development, where a researcher from Amgen talked about the development of a new anti-cancer drug, a drug used to treat, among other things, non-small cell lung cancer. And a big challenge there was being able to build up a complex molecule from simple building blocks, and to be able to build many different complex molecules to discover and develop a good drug. So organic chemists often write a reaction in sort of a utilitarian fashion as how we're going to make something or what procedures we're going to do. And so what I might end up doing is writing phenyl magnesium, that I take acetone in the first step, treat it with phenyl magnesium bromide. The pH is another way of writing that benzene ring. It's a shorthand standing for phenyl group, followed by treatment of water. Treatment with water is what we would call an aqueous workup. and that quenches or protonates the alkoxide anion, and the product of that reaction would then be the corresponding alcohol molecule. And this is a very nice way, the common theme that we will see in reactivity. So I'll just show you a couple of other examples with the first three organometallic reagents, with the Grignard reagent, with an organolithium reagent, and with an acetylide, and we're going to save cuprates for later. So I'll take acetophenone, another compound that by now should be familiar with you, familiar to you. I'll take acetophenone and treat it with methyl lithium, and then an aqueous workup with water or mild, very mild acid solution. And the product of this reaction is the exact same product. I've written it differently because I wrote the phenyl group, but you'll see it's the same molecule. In fact, this kind of comes back to a theme that often there are many different ways to synthesize a molecule from simpler building blocks. In the case of the acetophenone, you could have imagined it coming from benzene by a Friedel-Crafts acylation reaction with acetyl chloride and aluminum chloride. In the case of the phenyl Grignard reagent, you could have imagined it coming from benzene by electrophilic aromatic bromination, followed by generation of the Grignard reagent. And we'll see that in just a second for how we generate a Grignard reagent. Finally, I'm going to take one more example and again just show a different organometallic reagent. So I'll take 2-cyclohexenone. And let's treat it with our sodium acetylide. And I'll write it this way. I'll write the ionic structure of sodium acetylide because that's like how I like to think about it. And I'll write an aqueous workup. And in all of this, we can picture basically the same reactivity. We can picture the acetylide group adding to the carbonyl group. And the same would apply if we had an aldehyde or we had a ketone. We're going to come back to esters and other members of the carboxylic acid family in just a moment because we see special reactivity there. But as I said, your textbook throws a lot at you. So to generate a Grignard reagent, you go ahead and you take an alkyl halide or an aryl halide. You take a halogen compound, typically a bromide or an iodide. In some cases, a chloride, never a fluoride, however. And you take magnesium metal. Magnesium's a beautiful metal. It's sort of hard and comes in turnings. And although it reacts with air, it does so very slowly. So the turnings may have a little bit of an oxide layer on them, and you'll get a fresh surface of magnesium by sort of crushing them. And the Grignard reagents really need an ether solvent in which to generate them. The ether coordinates to the magnesium, although I'm not going to write it. So you can take diethyl ether is a common solvent. Tetrahydrofuran is another common solvent, and there are various other solvents that get used. But in all of these ether solvents, you will, if everything goes right, generate a Grignard reagent. Sometimes the reaction's a little hard to get started. If you took methyl iodide and subjected it to the same circumstances, the same reaction conditions, magnesium and diethyl ether, magnesium and THF for that matter, you would get methyl magnesium iodide. And you'll notice, although I wrote the name phenyl magnesium bromide and I haven't explicitly written methyl magnesium iodide, you can see the trend here. So I don't need to write it. I showed you butyl lithium before. And so I'll show you a typical way in which it's generated. You would take, say, butyl bromide, and you would treat it with lithium metal. And in the case of organolithium compounds, one of the quirks of them is they don't require an ether solvent. You can generate an organolithium compound in ether, but you can also generate it in hexane or other hydrocarbon solvents. So here's how we would generate an organolithium compound, specifically butyl lithium. Now, organic chemists, when we write reactions, often don't write balanced equations, and that can be confusing the first time around. So I'm going to write a balanced equation for you as well. If we take butyl bromide, 1-bromobutane, it reacts with 2 molecules of lithium to form butyl lithium plus lithium bromide. That compares to a Grignard reagent. It may not be that surprising. The metal is giving up its electrons. If you look at the periodic table, the alkali metals have 1 electron to give. The alkaline earth metals have 2 electrons to give. So ultimately, we need those 2 electrons to put onto that carbon, but 1 lithium isn't enough. And so here's an example of a balanced equation. Finally, hearkening back to chapter 12, when you first got to see acetylides, acetylene itself and various alkyl acetylenes are all relatively acidic. And so a strong base like sodium amide, NaNH2, will go ahead and deprotonate the acetylide, or deprotonate the acetylene like so. To contextualize this, pKa's are another theme that constantly runs in the background of our minds as organic chemists in understanding reactivity. I got a great question by email the other day about when a nucleophile adds to a carbonyl reversibly, when it adds irreversibly. And I said, well, generally, if the pKa of the conjugate base of the conjugate acid is greater than 25, addition is irreversible. If it's 25 or less with varying degrees, it's reversible. And this just sort of runs through my mind. So let's take a look at this acid-base reaction in a little bit more depth. So here's our amide anion of sodamide. Here's our alkyne. The amide anion pulls off a proton. We put our electrons back onto the acetylene, like so, to give us the acetylide anion plus ammonia. And guiding my thinking, this is an acid-base reaction, guiding my thinking on this, and as to why I'm just writing this arrow with not even an equilibrium, is that acetylene is far more acidic than ammonia. In other words, acetylene has a pKa, again, borrowing from your tables in your textbook, of about 25, whereas the conjugate base of the amide anion has a pKa of about 38. In other words, this reaction has an equilibrium that lies 10 to the 13th fold to the right. It's no contest. That amide just pulls off a proton. Sodium hydride is another base that we could use to pull off that proton. The pKa of the conjugate acid, hydrogen, H2, is about 35. And so this would be sort of a basic introduction to our organometallic reagents. Now, as a corollary to this, Organometallic reagents are strongly basic. So what that means is organometallic reagents react with water, they react with alcohols, they react with carboxylic acids. Anything that's even mildly acidic is going to quench them. So if I take butyl lithium and I add it to water, I go ahead and generate butane plus OH minus, or technically lithium hydroxide, I guess I could write. And if I want to think about the pKa's and why I'd write this reaction, I say, okay, water has a pKa of 15.7, whereas a carbon-hydrogen bond in an alkyl group, an sp3 hybridized carbon, has a pKa on the order of 50. If I do the same thing and consider, actually, this gets us into thinking a little bit more about generating organometallic reagents. If I take phenylacetylene and I treat it with N-butyl lithium, we already said, okay, pKa for the conjugate acid of organolithium is of an alkyl lithium is 50, a butyl lithium is 50. pKa of an acetylene is 25. And so that very, very, very basic organolithium reagent, butyl lithium, pulls off the only very basic proton of acetylene to generate lithium phenylacetylide. All right, continuing with this theme of acids and bases, if we come back to our poor phenyl magnesium bromide, and instead of giving it an opportunity to react with a carbonyl compound, we throw an alcohol at it like ethanol. Ethanol is just like water in its pKa. It's about 16. It's, while not an acid, it's weakly acidic. And so again, that very strongly basic Grignard reagent is going to pull off that proton, and we're going to get benzene and ethyl magnesium bromide. And again, if you prefer to write an ionic structure, just as I did in our initial example, CH3CH2O minus, MgBr plus, be my guess. Finally, just to complete some various examples that you might think about or encounter, I'll take that lithium phenylacetylide. If we take a carboxylic acid, now remember the pK of carboxylic acid really gets into that sort of not weak, you know, it's a weak acid, but it's not as weak an acid as ethanol. pKa is 4 or 5. Now we can really think of this as protonating the acetylide anion, or the lithium acetylide. Like so. Thoughts or questions at this point? Yeah. Well, in terms, okay, that's a great question. The subtext of the question that was asked is, if I wrote this reaction here, if I wrote that reaction, would it be correct if I didn't write 2Li? Absolutely. And again, this is how sort of organic chemists communicate. Now, in practice, if I only used 1 mole of lithium metal per mole of bromobutane, I would only generate half a mole of butyl lithium. I'd still have half a mole of butyl bromide. And so if I was saying, oh, okay, now I've added in my ketone and I only got half a mole of product, why didn't I get more? It would be, oh, I didn't use enough lithium. But again, in terms of writing this as an equation, as a shorthand, yeah, it sure would be correct. Yeah, another question. Uh-huh. So to be honest, really the flavor where you would have a fully ionic bond is going to really come down largely to the alkali metals, sodium and potassium. You know, the electronegativity of sodium and potassium is a little less, they're a little more of electropositive than lithium, but the bonding really is substantially less covalent. And in fact, this is one of the reasons why organolithium compounds are generally so useful in synthesis versus, say, organosodium compounds. Organosodium compounds are very reactive, relatively unstable, much more ionic in character. And really only in the case of acetylides would one be using sodium. So lithium is the big crowd pleaser among the alkali metals, and magnesium is the big crowd pleaser among the alkaline earth metals. Does that help? So I'm not sure I'm following. You're writing this, you're looking here or here. So top part or the bottom? Top part. So at this point here, we have no water. We carry out this reaction under rigorously anhydrous conditions. So there's no source of protons. If I tried to cheat and run the reaction in water and say, I'm going to do a twofer, I'll go ahead and I'll have my Grignard reagent and have it form the alkoxide and then quench it to get the alcohol all at once. The Grignard reagent would spontaneously react with water, just as I've shown down here, which was sort of done as a cautionary note of basically, if you take your Grignard reagent or your organolithium reagent and have any water present, it will react. And we're going to stick a pin in that because I'm going to introduce protecting groups in just a moment. You're going to see how we need to make use of that ability to hide an OH group. Other questions? All right, let us now move on to the idea of building up organic molecules. So one of the powerful things about organic chemistry is you can start with very simple molecules and make complex molecules. So I'm going to write a question that would be very typical of what I might write on an exam, but not because an exam is about testing, but because this is about thinking processes. So let's say I asked you to propose a synthesis of 2-phenyl, 2-heptanol, starting only with compounds containing 6 carbon atoms or fewer. This is not exactly the way, say, Matt or Jackson and Mai would think, because you have a much bigger menu of compounds available, but it's a nice sort of subset of the thought of processes of organic chemists. It also gives an expectation of what I would expect you to be able to figure out in terms of nomenclature. So, okay, let's start with our target molecule, 2-phenyl, 2-heptanol, and then we'll apply the concept of retrosynthetic analysis to figure out how we can build that. So that's 2-phenyl, 2-heptanol, and we'll take a look at how we can build it. The pH, of course, is just a shorthand for benzene. Yes, Mai. Sometimes. So the question is, as I just said, is this something I would expect a level of basic competency on, being able to write a structure from a name like this? Absolutely. So the short answer is probably yes. This is a simple compound. And I've been going along and kind of writing the names of simple compounds that I would consider basic competency. Okay, so we look at this molecule and we realize that in the potential to synthesize it, we've learned about reactions that form carbon-carbon bonds, and the product of that reaction ends up being an alcohol. So we can look at this molecule and say, oh, okay, any of these carbon-carbon bonds could be formed by the addition of an organometallic reagent to a carbonyl compound. Let's go ahead and use that as a thought process. And remember, when I'm writing a retrosynthetic analysis, I'm not writing the answer yet. That's not an answer. It's just my thought processes. And so I'll show my process of thinking backwards and say, okay, well, I can't start with anything bigger than a phenyl group. So let's go ahead and think our way back to a phenyl Grignard reagent, or phenyl lithium, and a carbonyl compound, namely 2-heptanone. Now, 2-heptanone still contains 7 carbon atoms. And thus far, I haven't learned a reaction that would form a ketone directly, but I know that I can make a ketone by oxidation of an alcohol. And so we could think our way back and say, okay, whoops, iPad is trying to outsmart me here. I could go ahead and envision making that ketone, synthesizing that ketone from an alcohol, from 2-heptanol. And now, again, in my thought processes, I could go ahead and say, oh, okay, again, I could see I could form either of these 2 bonds. In other words, I could go ahead and have a 6-carbon aldehyde, heptanal, and add in a methyl Grignard reagent or methyl lithium, or I could have a 2-carbon aldehyde, acid aldehyde, and add in a 5-carbon organolithium compound or Grignard, either pentyl, N-pentyl magnesium bromide or N-pentyl lithium. But I'm going to go and split this into the reaction where we start with hexanal. And methyl magnesium iodide. So this is an example of what I would call a retrosynthetic analysis. It's not the answer to the problem, but it is the thought processes that got us there. So having sort of done my scratch work, having done my thinking, now I'm going to actually answer the question as posed, and I will go ahead and say, okay, let's answer the question. I'm going to start with hexanal, and I'll treat it with methyl magnesium iodide. I could have used methyl magnesium bromide. I could have used methyl lithium. I'll go ahead, I'll carry out an aqueous workup. That will take me to my heptanol, my 2-heptanol. We learned in chapter 12 of your textbook of the 6th edition of your textbook, we've learned a number of oxidizing agents that can oxidize an alcohol to a ketone. Potassium dichromate. Chromium-6 is a very good oxidizing agent. Your textbook has a nice treatment of oxidations. Potassium dichromate or chromium trioxide, CrO3, in sulfuric acid and water is a good way to carry out this oxidation reaction. And by good, I mean good but. Chromium-6 is carcinogenic and toxic. And these days, although this is what your textbook has taught because they're giving you sort of a limited menu, these days chemists often use other oxidizing agents that don't have chromium-6. Another chromium-6 oxidizing agent that you learned about in your textbook was Pcc Pyridinium Chlorochromate, which is a protonated pyridine with a CrO3Cl- anion. It's another chromium-6 reagent. So I could write or Pcc, but I wouldn't need to or want to. That's another reasonable oxidizing agent. Pcc is cool because if you're oxidizing a primary alcohol like ethanol, you can stop at the aldehyde stage because to oxidize to the acid takes water. Whereas if I start with an aldehyde, an alcohol like ethanol, and I oxidize it with chromic acid, with potassium dichromate in sulfuric acid and water, it's going to oxidize all the way to acetic acid. So anyway, then I'll take my favorite Grignard reagent or organolithium reagent with a phenyl group in it. I'll take phenyl magnesium bromide and again carry out an aqueous workup. And now I've gone ahead and answered the question and generated the product of reaction. Questions or thoughts at this point? All right, in part because I want to show different modalities of reaction, I'm going to ask or put forth sort of another thought experiment. Propose a synthesis of phenyl acid aldehyde from starting only with compounds containing 6 atoms or fewer. All right, so again, figuring out what the structure is of this molecule is part of our job here. So this is phenylacetaldehyde. I don't need a number on that because if it were at the 1 position instead of the 2 position, I could call it 2-phenylacetaldehyde, but I don't need to, because if it were at the 1 position, it wouldn't be an aldehyde, it would be acetophenone. Okay, so again, right now, I'm not able to, I know reactions that make alcohols, and so I could say, well, I don't really know where to begin. I'm guessing that somehow I've got to be able to form this bond over here, but let's take a look at reactions. And this is a modality of reaction that you've seen before. So let's imagine for a moment that we go back to the alcohol. And really what I'm driving at here is if, again, we think our way back to the alcohol in a retrosynthetic analysis and hearken back to, well, first of all, what we've read in this chapter, but also what we've learned about epoxides, we could say, okay, I need some sort of phenyl nucleophile. I'll choose phenyl lithium this time, plus an epoxide, specifically the epoxide that's commonly called ethylene oxide. So we've learned about the reaction of organometallic, well, we've learned about the reaction of other nucleophiles, including, I believe, acetylides earlier on with epoxides. And basically, the nucleophile can open that ether ring. Normally, ethers don't react with alkylithium reagents or Grignard reagents, but a 3-membered ring is very strange. Cyclopropane with carbon analog has 27 kilocalories per mole of ring strain, meaning that those bond angles are so bad that the ring really is quite strained and wants to pop open. For comparison, remember, when I talked about the aromaticity of benzene and said it's no way like an alkene, that's 36 kilocalories per mole of special resonance stabilization. So 27, 36, those are big numbers. So just as benzene has a lot of special stabilization, ethylene oxide has a lot of special destabilization. And so a carbon nucleophile can pop open an epoxide to give an alkoxide with a metal counterion. But this reaction allows us to add in 2 carbons. You certainly could solve this problem by adding in, doing this reaction in other ways, but this is a very nice and quick way to do this. And so again, those are my thought processes. If I now go in the forward direction and actually answer the question asked, if I take phenyl lithium, or for that matter, phenyl magnesium bromide or phenyl magnesium iodide, and I treat it with ethylene oxide followed by an aqueous workup, I get over to the corresponding alcohol after the aqueous workup. If I then oxidize that alcohol, and now you really do need to use Pcc to stop at the alcohol, to stop at the aldehyde and not go all the way to the carboxylic acid, not go to phenylacetic acid. Now I've got, now I've got the corresponding aldehyde that I wanted. So that's an example of thinking our way through a problem retrosynthetically and building up a more complex molecule. In your textbook, you're going to learn about various other reactions. For example, you'll learn about very mild oxidizing agents to oxidize aldehydes to carboxylic acids, for example, silver oxide in aqueous ammonia. And of course, you could also use many other oxidizing agents to do this. You could use potassium dichromate or chromium trioxide in water and sulfuric acid. You could use K2CrO3, water and sulfuric acid. Doesn't really matter the order that I write these. All of these reactions will take an aldehyde to a carboxylic acid. So you'll become flexible with reduction and oxidation. For reductions, you learned about borohydride reagents, reducing carbonyl compounds. You've read about catalytic hydrogenation. All right, at this point, I want to introduce another concept that's very important in synthetic organic chemistry, namely the concept of protecting groups. Protecting groups can be used to hide, and I'll put that in quotes, a reactive group in order to permit the desired reaction. I'll say a desired reaction. And I think your textbook wants to start you with a limited menu, which is good because I have a book that's 800 pages thick titled Protecting Groups in Organic Synthesis. And so there's a whole big area, but the textbook wants to give you just a little flavor of this. So let me show you a conundrum. And let's imagine for a moment that I was in my mind's eye wanting to go ahead and make a Grignard reagent like this and say, add that Grignard reagent to benzaldehyde to go ahead and make the following diol. Molecule containing 2 alcohol groups. And you said, this is where I wanted to go. And I did this, but I thought for a moment and I realized, wait a second, back earlier, he just said that Grignard reagents are very basic. pKa of the conjugate acid of this Grignard reagent is about 16, is about 50 because it's an alkyl group. You have an OH group in the molecule that's comparatively acidic, that's pKa of 16. That Grignard reagent is going to annihilate itself. It's going to not be stable, and so I'm not going to be able to do this reaction. In other words, if I tried to generate that Grignard reagent by taking the corresponding bromoalcohol and treating it with magnesium in ether, sure, I might transiently generate the desired Grignard reagent, but immediately it would go ahead and annihilate itself. I'll write the CH3 group explicitly to indicate the molecule has annihilated itself. And I would get the magnesium alkoxide. In other words, I can't make that Grignard reagent. I've got to do something to hide that alcohol so it doesn't get involved in this reaction. And your textbook introduces one protecting group, which is a versatile go-to protecting group for alcohols, the Tert-Butyl Dimethyl siloprotecting group, great protecting group. By the way, I believe it was introduced by E.J. Corey, who is the academic father of Jan Smith. In other words, the person with whom she earned her Ph.D. He also happens to be my academic grandfather. So tert-butyl dimethyl silyl-chloride really is a nice protecting group. And you'll see a lot of examples from the Corey laboratory in this textbook, in part because E.J. Corey won the Nobel Prize in 1990 in the area of organic synthesis and is a major contributor, a major thought leader in the area of synthetic organic chemistry, and in part because Jan Smith uses his contributions a lot. So tert-butyl dimethyl silyl-chloride, in the presence of a base, and the one that is invariably used is imidazole. You generate the corresponding TBDMS ether, tert-butyl dimethyl silyl ether. And that TBDMS ether, I'll just write a TBDMS ether, TBDMS ether. That TBDMS ether now has hidden that alcohol group. By the way, if I want to fault the textbook on one thing, it would be not showing you the structures of many of the reagents and just leaving them as names. This is imidazole. It's just a mild base. I didn't show you Pcc, but that's another one they name. So what that allows us to do is to hide the alcohol and thus now generate a Grignard reagent. And so if I treat this TBDMS ether with magnesium metal in ether, now I have no acidic alcohol lying around. And so I can go ahead and generate my Grignard reagent. And then I can go ahead and add an aldehyde to it to carry out the Grignard reaction that I wanted to do. And that aldehyde is benzaldehyde here. And so I'll add benzaldehyde and carry out an aqueous workup. And now the product of reaction is going to be the TBDMS ether. And the very last reaction that Smith gives you is the removal of the TBDMS group with an organic salt, a fluoride anion, a fluoride source that dissolves in organic solvents, tetrabutyl ammonium fluoride, often dissolved in THF with a little bit of water in there to provide a proton. Fluorine and silicon just love each other. Silicon forms very strong bonds with fluorine. So the fluorine actually acts as a nucleophile and attacks the silicon. I won't write out the details of the mechanism, but the result is that the alcohol is now liberated. And so through this strategy, through the use of protecting groups, we have now generated the desired product. All right, I want to move on at this point to what I put aside before, which is the reaction of the carboxylic acid family with organometallic reagents, and specifically esters and acid chlorides. We already saw that the primary reaction of a carboxylic acid with an organometallic reagent is acid-base chemistry. That carboxylic acid will get deprotonated. It will donate a proton and quench the organometallic reagent. But if I have some ester, which I'll write generically as R carbonyl OR prime, and I have some organometallic reagent, really meaning some Grignard organolithium or alkyl metal reagent. And I say, wait a second, okay, he taught me about addition of nucleophiles to carbonyl compounds. Maybe I'll go ahead and get a ketone and generate the corresponding metal alkoxide. And you'd look and you'd say, that's not quite right. And the problem is that ketones are even more reactive than esters. In other words, I can't stop at just one. It's like potato chips. Once you have one, you got to eat a second, third, in this case, just a second. So let's take the abstract to the concrete. If I take ethyl benzoate and I treat it with methyl lithium, we go ahead, and I want to think our way through this. We go ahead, so I'm going to write a little bit of a mechanism. We go ahead and we form a tetrahedral intermediate, like so. I'm not writing all of my curved arrows because by now you're good at this. Okay, that tetrahedral intermediate breaks down. We lose ethoxide anion, we lose ETO minus. And at that point, we get to the ketone. We get to acetophenone. But as I just said, the ketone is more reactive. And so another molecule of methyl lithium comes along, and if it has a choice to make, do I react with that ketone or do I react with the ester? It reacts with the ketone, it reacts with the acetophenone, and the product of the reaction now is that I've added two equivalents. If it's methyl lithium that I'm using, I've now gone ahead and formed the lithium alkoxide. And just as in the case of generating butyl lithium or trying to generate it with only 1 molar equivalent of lithium instead of 2, I would only get half as much butyl lithium. In this case, we're in the same situation. If I used only 1 molar equivalent of methyl lithium instead of 2, we'd mostly get the corresponding 2-phenyl 2-propanol, or the corresponding alkoxide, if I didn't do a workup, and still have plenty of ethyl benzoate left over, and we would not go and generate the desired product. We wouldn't generate that ketone that I started out by saying, oh, I'm trying to make that. So taking this maybe from the abstract to the concrete, since this is sort of our thought process, I'll say this is our thinking. If we go ahead and pose a question like, what happens if I treat ethyl benzoate with methyl lithium and water? The best way of thinking might be, okay, I'm going to go ahead and generate the corresponding alcohol. And if I'm a good person, organic chemists often end up ignoring byproducts of reaction. If I'm a good person, I will also think my way through and say the other byproduct of reaction is ethanol. And this is the same whether we go ahead and we do this for a carboxylic acid or an acid chloride. Acid chlorides are super reactive, but are also hard to stop at the ketone stage. So if I went ahead and did this with benzoyl chloride, I would be in a very similar situation. In other words, it's really not going to stop at one equivalent. Your textbook kind of gives you the simple answer on carboxylic acids, which is that organometallic reagents, like specifically organolithium, well, it gives you that organometallic reagents deprotonate them. That's the simple answer. You get the carboxylate salt. The more complicated answer is, organolithium reagents under the right conditions can further add to the carboxylate salt to generate a tetrahedral intermediate that doesn't break down. In some cases, you can get the ketone. Your textbook skirts around that, so I'm not going to go into that. Your textbook also skirts around the reaction of amides, which in some cases is also the same, where you can stop at a tetrahedral intermediate, and then on workup, it breaks down to the ketone. But I will happily skirt around it. We've covered a lot of ground up until this point. This is a good point for me to stop and ask for questions. Thoughts? So I want to, I prefer you actually keep the mechanisms to yourself. So no, I actually don't want mechanisms written out. It's sort of your thought processes, kind of like the retrosynthetic analysis. The short answer would be, you're welcome to write your work, show your thinking, but you're not expected to. If the thinking is sloppy, sometimes, unfortunately, it may lead to me or one of the TAs realizing that you really knew less than you thought. On the other hand, it may help us clarify some confusion, but the short answer is no, I wouldn't do it. As long as we're mentioning exams, again, although you absolutely don't need to, everyone is welcome to look at old exams from past years to go ahead and see how questions are often posed if it makes you feel more comfortable. But the biggest thing, particularly this year, I've always emphasized this, but I really wanted to incentivize this because you and I want the same thing. You want to do well in the course. I want you to learn organic chemistry well. That's the same thing. So, as I've said from the get-go, the most important thing you can do to learn organic chemistry is to work problems. You absolutely can't. And that's not look at the problem, look at the answer. It's actually look at the problem, don't look at anything. Right? Flip back to the textbook, try to figure out what they're talking about, right? And so, as I said, to incentivize this, because again, you want to do well, I want you to learn organic chemistry. To incentivize this, about half of the exams are going to be adapted from, not taken verbatim, but referencing specific problems from the homework or discussion section. So both my goals and your goals are going to be achieved. So come along with me on this. Other questions, Mike? There will not be scratch paper provided. I don't think I typically do that. What I do for scratch work is I use the backs of pages. I think they do get scanned, but we typically don't look at them. So what I do is I just take the back of the previous page and go ahead and we'll write my thinking, or I'll write my work on the back of the page. All right. Let us move on, because I've said that organocuprate reagents are special for a number of reasons in their reactivity. And now I'd like to sort of unveil that specialness and also teach you some new modalities of reactivity. So let's start with the generation of organocuprate reagents. Remember, the example I gave you was lithium dimethyl cuprate. And I dodged at that point how you prepare it. The way you prepare it is you take 2 equivalents of an organolithium compound and you treat, typically it would be cuprous iodide with it, copper 1 iodide, and that will get you to lithium dimethyl cuprate, which I've written like so. Organic chemists are notoriously bad at balancing equations, but if you want to balance your equation, the other product of this reaction would be lithium iodide. And if you want to think more about this reagent, you can think of it as a dimethyl cuprate anion with a lithium counterion. In other words, an ionic compound like this with polar copper alkyl bonds. And organocuprates are special. They're less ionic, they're more polar covalent in their metal alkyl character, and they have some special modes of reactivity. So one of the modes of reactivity that's special is you can go ahead and take an acid chloride like benzoyl chloride. You can't do this with an ester, but you can take an acid chloride and treat it with a dialkyl cuprate like lithium dimethyl cuprate, and then do an aqueous workup. And in this case, for various reasons, you can stop at the acid chloride, at the ketone. In other words, the cuprate's reactivity is attenuated. And even though acid chloride and they're reactive enough to easily add to an acid chloride, but generally don't add directly to carbonyl groups. So I'll write that as cuprates generally don't add to carbonyl groups. All right, now there's one very special modality of reaction of organocuprates, which your textbook brings in, and it's going to be sort of a start of things we're going to continue to see later on. And this is in the reactivity of alpha beta unsaturated compounds. So I want to introduce the alpha beta unsaturated compound 2-cyclohexenone. I believe I started with that as an example with the phenylacetylene or with the lithium acetylide reaction. And this is an exemplar of a broad class of compounds, as I said, called alpha beta unsaturated carbonyl compounds. And you'll notice in these two different nomenclatures, we're having two different ways of thinking about this molecule. In terms of the nomenclature of the 2 position, you'd say, okay, the carbonyl position is number 1. This position 1 over where our double bond is number 2, hence the nomenclature. In terms of the nomenclature alpha beta unsaturated carbonyl compound, we'd say, okay, the position next to a carbonyl is an alpha position. That's an alpha position. That's an alpha position. And we have one beyond that, a beta position. So the 3 position is also referred to as the beta position. And so this is an alpha beta unsaturated carbonyl compound. Now, cyclohexenone and other alpha beta unsaturated carbonyl compounds have very special reactivity with cuprates. And so if I take our lithium dimethyl cuprate and I treat our cyclohexenone with it, and then I carry out an aqueous workup, what happens is the methyl group adds to the beta position. So we get 3-methyl cyclohexanone. Now, alpha beta unsaturated carbonyl compounds bring you one extra special resonance structure. So we already learned in thinking about carbonyl compounds that we can think about the oxygen carbon bond as being a polar covalent bond, a covalent bond where although electrons are shared, they're not shared and shared alike. In other words, we have a partial negative charge on the carbon and a partial positive charge on, or partial negative charge on the oxygen and a partial positive charge on the carbon. We can think of a third resonance structure now where we have allylic resonance like so, and we have positive charge character over here as well. Collectively, these make up a more complete picture of the molecule. If you need a crutch, if you need curved arrows to help you think about this, I'll draw my little crutch of saying, okay, I can imagine those electrons flowing to get me from one resonance structure to the other. I can imagine those electrons flowing, but generally I prefer that one just keep this privately in one's head and not use this crutch. Nevertheless, this reactivity, this resonance structure helps us think about why an alpha beta unsaturated carbonyl compound should be electrophilic at the beta position. In other words, we can think of our cuprate anion as transferring a methyl group, and we can picture that that methyl group, which wouldn't normally add to a ketone, it wouldn't normally add to cyclohexanone, goes ahead and adds and attacks the beta position. That pushes electrons on up, and I'll be a good person. I'll draw in my lone pairs of electrons. That goes ahead and takes us all the way over to here. And you should be good enough at pushing your arrows at this point that you should be able to do this on your own. And now this has introduced a new species that we call an enolate. If this seems a lot to take in now, don't worry, we're going to be seeing enolates again as we progress through the chemistry of carbonyl compounds, particularly talking about reactivity. For now, just know that there are two resonance structures that collectively work well to describe the structure of an enolate to present a more complete picture of the structure of an enolate. One with the negative charge on the oxygen and one with the negative charge on the carbon. And that helps us explain how when we treat our product of addition with water, we now protonate the alpha position. And so putting all of this together the way a synthetic organic chemist would, taking 2-cyclohexanone and first treating it with lithium dimethyl cuprate, and then treating that with water gives rise to conjugate addition of a methyl group. All right, one last odd and end I'd like to pick up. Your textbook gives a lot of nice reactions. You should read it on your own and learn about things. But the last reaction I'll show you is that organometallic compounds, specifically organolithium compounds, Grignard reagents, alkyl metal acetylides, all react with carbon dioxide. And this is actually a nice way to add a carbon and make a carboxylic acid. Just like a carbonyl is reactive toward an organometallic reagent, carbon dioxide is reactive. Carbon dioxide contains 2 carbonyl groups, and your organometallic reagent can add to the carbonyl group, pushing electrons onto the oxygen to give you the carboxylate. So if I take toluene magnesium bromide, and again, I'm just playing and writing various molecules, and I treat it with first magnesium in diethyl ether, and then I go ahead and I add carbon dioxide. Sometimes you can even throw in chunks of dry ice into your reaction mixture to do it, or you can add carbon dioxide gas. And then I add some acid because we're going to want to protonate that carboxylic acid. So I add a little HCl in water or sulfuric acid in water. I want to protonate that carboxylate. I get all the way to toluic acid. So that's a nice way to add one carbon and build up a molecule and form a carboxylic acid. So on that note, I think I'm going to close our discussion of chapter 17. It's a rich chapter with lots of examples. I have, if you haven't started on it, I have a lovely homework set for you to work through. And just like going to the gym, lifting weights that makes you stronger, or going out and running makes you have more endurance, you'll be much better and much stronger at solving organic chemistry problems once you've done your exercise. I will look forward to seeing you on Tuesday. Have a great weekend.